All right, so let's carry on. Just one little note from one of your colleagues. Actually, I had an R prime in this equation here. This is wrong, right? So this is a local equation. This was curl of B at a certain point in space-time actually, is really proportional to the current at that point in space. Okay? And also, just to be absolutely clear, maybe as after a coffee or something, after a break, what did we just do? What just happened? Okay, so what just happened? Well, you were informed by your colleague experimentalists 2 centuries ago that magnetic fields are to be computed according to the prescription codified in the Biot-Savart law. Okay, it's just they can show you all the experiments. It's completely compelling with a little assumption of simplicity that indeed the exponent is 1 over distance squared rather than 2.01 and whatnot. You get this law. And now, if we look at this law, we can, if we feel absolutely powerful with integrals and whatnot, that this is completely sufficient. It is completely sufficient because we have an explicit expression for B given as this, in general, quite complicated integral, because in order to know B at a certain point in space, I need to know the current at every single point in space. Maybe this one is the one to look at. To know the magnetic field at a certain point in space, I need to know the current density everywhere. Okay? So that's the complicated thing. So it's an integral equation. But then you might, through your personal experiences, relationships, family ties, whatever, business dealings and whatnot, you might have a preference for differential equations of a local nature rather than integral equations of a non-local nature. So then you ask the question, hey, is it possible to write an equivalent set of equations containing absolutely the same information, but in differential form instead of integral form, and more or less of local form? I look at something somewhere, and in order to know the characteristics, I just need to look here. I don't need to know what happens elsewhere. The answer to this is yes. And the answer to this is also, that's what we did the first hour. We transformed the integral representation of the magnetic field into a set of differential conditions for the magnetic field. But these differential conditions, the nameless law, div B is 0, and Ampere's law, that the curl of B is proportional to the local current, they carry absolutely exactly the same information as Biot-Savart itself. From that point onwards, you can kind of toss Biot-Savart. And you see the advantage here also, because these equations are local. Okay, so that's a very, very important thing. So that's what we did the first hour.